Hello everyone, welcome back to the online NPTEL certification course on aquatic geochemistry. This is your fifth lecture. I had already been discussing the hydrological cycle in the previous lecture and I will be continue discussing it in this lecture as well. So, in the last lecture I was discussing about the processes that controls or maintains the hydrological cycle, such as evaporation, transpiration, condensation, precipitation, runoff and infiltration and evapotranspiration. And in this image that I am showing on the right side, you will see the principal storage boxes and the pathways are given in the form of arrows. Okay. There is a heavy dashed line that sends the boundary of the watershed of the region. Okay. So, first things we have is energy. So, due to energy there will be a lot of evaporation. So, we will start from here. So, we will start from precipitation. So, after evaporation from the oceans and all, there will be condensation and precipitation happening. Now, precipitation can come in the form of rain or it can come in the form of snow. The first thing in the catchment that intercepts the rain will be by the canopy of the trees, and there will be some interception storage. That means a very small fraction of that rainfall will get stored on the the leaves and all that. So, canopy interception storage, and through fall and via stem flow it will come down, right. It will across the it will fall through the trees and as stem flow through the along the bark of the tree, it will, that is called stem flow, it will come down, right. And there is a loss of water in this process. This process is basically called the interception loss. That means, due to some evapotranspiration, again this water that is being intercepted by the canopy, they will again be lost to the atmosphere. If it is coming in the form of snow, it will form as snow and it will form the snow pack. Then it can start melting if there is energy available, or if it is a hotter climate, then it will start melting, and of course, if it is coming as rainfall, it is coming as rainfall. Then there will be surface detention, that means it will get retained in the surface of the earth, right. If it infiltrates into the soil, if it infiltrates onto the land surface, it will go into this soil moisture storage, right. Now, from the soil moisture also it can go as loss as transpiration. So, from soil moisture the plants will be uptaking the soil and they will transpire. So, there is a loss here. So, it again you can see the transpiration process, it is moving out and going into the atmosphere. If there is excess rainfall, then more than infiltration there will be overland flow. That means, water is now saturated, it will not move any further down through the soil, it will now flow over the land and it will form small rivulets, and that can form small streams and can enter the lakes and large streams, right. Now, from the soil moisture component, it can percolate. If it percolates, it reaches the groundwater storage, right, or it can again through capillary forces and all that, from the groundwater storage there is capillary rise and it can again move to the topsoils, and where again it is uptaken by plants and it can get lost through transpiration and evapotranspiration. From groundwater can also flow, due to the slope of the topography and all, it will flow and it can finally enter into the streams, or it can also enter the lakes, or it can give into the larger runoff. Now, when I am saying the larger runoff, that means now this runoff is going outside this catchment boundary. Okay. So, outside of this catchment boundary it is going out. Now, this runoff can either flow into another very large system which thereafter goes back into the ocean. So, this is how we can break down the hydrological cycle from the global scale, and we can observe it in the local scale, right. And in this hydrological cycle, there is different phases and there are multiple cycles that is occurring. It is not like a continuous one process, right. There is multiple phases, multiple smaller cycles happening. So, one such cycle is the ocean atmosphere cycle, okay. And of course, as I said, we always begin from the ocean. So, the sun's energy evaporates the water from the ocean, okay, or it can due to sublimation, which is a very minor contribution, but it is still there from the ice caps. That evaporation, all the water vapor is getting into the atmosphere. Now, that atmosphere, due to air currents and all that, they will move into cooler areas, right. There will be due to this difference in heating, there will be pressure differences. Due to pressure differences, the air masses will be moving from an area of high pressure to low pressure. So, gradients will be created and all that. Now, wherever the masses are cooled, there condensation will happen. Condensation, if goes beyond the capacity level or the carrying capacity of the atmosphere, it will start precipitation. Now, once this precipitation starts forming, then this if it is happening in the oceans, which is like 80 to 90% of the time, the oceans are actually receiving back the water that was actually evaporated, then this cycle gets completed. And it is said that once a water molecule is evaporated from the ocean, it stays in the atmosphere for roughly 10 days, right. So, 10 days is the residence time of water in the atmosphere. So, either it will again these values of resident times are averaged values, right. It need not mean that if I fingerprint a particular molecule, I will see that it will return to the ocean after 10 days. It is an average value that we take for all our global calculations. So, this water from the oceans going back to the atmosphere and from the atmosphere back to the oceans, this forms the ocean atmosphere cycle. Atmosphere and terrestrial cycle. What is this atmosphere terrestrial cycle? Again, once this air water vapor in the air mass moves towards the land, right, and there it precipitates, then it starts the atmosphere terrestrial cycle. So, this precipitation that is forming either in the form of rainfall or in the form of snowfall, that happens, right. So, if it is in the form of snowfall, it can get stored as snowpacks, or if it is a stably cold region, then it can form bigger it can form bigger ice packs, and that can lead to the formation of ice and larger bodies like glacier bodies and all that. And they, when it melts during the warmer seasons, or if it is already raining, okay, then it will enter into the terrestrial system, right. So, it will enter into the land, it will enter into the river system, it will enter into the lake system, it will enter into the terrestrial aquatic system overall. Okay. And again, from this terrestrial aquatic system, a significant proportion of this water will again get evaporated and return back to the atmosphere, right. So, when it gets evaporated, and this is one of the largest so terrestrial heat, because the land gets heated much more, a lot of water that is falling on the landform gets again evapotranspired and it is released back into atmosphere itself. So, once it is again going back into atmosphere, this cycle gets completed. Okay. And the important part of this cycles, the processes that are extremely important is infiltration, how much is the runoff that is being generated, how much overland flow is being generated, and how much evapotranspiration losses are happening. Moving into another sub cycle, that is the surface water and groundwater cycle, right. Now, some of the water that infiltrates into the ground, okay, and it replenishes the aquifers and all, okay, there is some water that is stored into the aquifer system, and if it is deep groundwater, it can get stored for a very long time, right. But if it is in the shallow groundwater, it can it can easily be if there is a valley, okay, if the aquifer meets a valley and there is a pressure difference, there is a pressure gradient created, the aquifer will release its water to the river channels, right. So, this movement of water from the surface water to the groundwater and back into the system, this continues, right. So, again the river water, it will go into the ocean, again the ocean will start evaporation and all that, but this is a smaller cycle, that is the surface water and the groundwater cycle. Please understand that groundwater, in the shallow groundwater, the fate of most shallow groundwater is the streams or lakes. Okay. The fate of deep groundwater cannot be depends on the topography again of the region. It can always it can stay stable like that for thousands of years, or in even longer very long time scales, but the fate of shallow groundwater systems, which is more being used by humans and all that, their fate is finally the surface water environments, that is a lake water or river water. Now, after we have seen these smaller sub cycles, okay, there are certain highlights that I would like you to note, and that is the oceans, they lose more water by evaporation than they gain by precipitation. So, what did I say? I have said this previously also, that 80 to 90% of what is evaporating, right, is coming back as precipitation. Okay. So, there is a difference between the amount that is evaporating and the amount that they are receiving back directly as precipitation. But does that mean that the oceans are gradually shrinking? No, it does not mean that. It just means that there is a difference generated between these stocks of amount of water lost by evaporation and amount of water gained by direct precipitation over the oceans. Also, the oceans receive 70% of the global precipitation and contributes 85% of the global evapotranspiration. That means, water, how much water is just being evaporated from the surface of the ocean, that is the the balance that they are talking about. Land surfaces receive more water as precipitation than they lose by evapotranspiration. So, there is always a net storage of water over the land. In the continental part of the cycle, the precipitated water is recycled by evapotranspiration a number of times before it returns to the oceans as rivers and groundwater runoff. Okay. So, in the continent, so as I said, in the terrestrial cycle, once the water enters the terrestrial region, then it gets recycled, local recycling of water, and that smaller sub cycle and much smaller cycles are happening, that makes it recycle many number of times then it what finally returns to the ocean. So, if there is a water molecule that is coming onto the land form, it gets recycled much more times, and then finally it leaves the system to return back to the ocean. The excess of water on land returns to the oceans as runoff balancing the deficit in the ocean atmosphere exchange. So, this is the answer to the to the question that may be rising from point number 1, that whether our oceans are gradually losing water. No, they are not losing water. Whatever excess is from the land via rivers, via groundwater, that is going back into the oceans, and there is therefore balancing the deficit between the atmosphere and the ocean exchange. And this hydrological cycle, why am I talking about the hydrological cycle in a aquatic geochemistry course? This is because you will get to see the stocks, you will get to see the volumes, you will get to see the fluxes. This, what do I mean by flux? Flux is the movement of a particular of any particular substance. It can be particulate matter, it can be dissolved particular metal, it can be any kind of contaminant. Okay. So, flux that is volume, that is a concentration per unit volume, that kind of and it has to be in a particular time scale also. So, either it is in per year or tens of years or things like that. So, that flux controls the global elemental budgets, right. Now, the hydrologic cycle is responsible for 2 important geological processes, controlling these 2 important processes over earth, and that one is weathering and erosion. Now, water is an extremely important agent for weathering and erosion. I think I will explain their importance in our lecture on weathering. And this hydrological cycle actually controls the processes and the transformations and the reactions that all the elements are being that they are part of during the pathway of water from one reservoir to another reservoir, from one aquatic environment to another different kind of aquatic environment. It controls the cycling of elements. So, basically the global hydrological cycle controls the biogeochemical cycling of elements across the entire globe, right. And this is summarizing the global scale and the catchment scale. So, in the global scale you have the atmospheric system, you have the earth system, and you have the ocean system. Now, by the earth system I mean the earth's terrestrial system. Okay. So, the atmospheric system, it evaporates water, and it starts precipitation. So, there is precipitation happening. So, from the atmosphere it precipitates, it falls onto the terrestrial system, again it comes back to the atmosphere by evapotranspiration. From the terrestrial system through river flow it can go to the ocean system, and again through groundwater flow it can go to the ocean system. Again from the ocean system by evaporation it will go to the atmosphere. Also directly from the atmosphere it will go to the ocean by precipitation. So, this is the scale in terms of global scale if you have to divide. In the catchment scale there is much many processes, as you can see there is much more finer details has to be added. So, firstly there is the vegetation system, all kinds of plants and surface vegetation and all that is there. Then there is a structural system. What do you mean by structural system? That means the earth's structure. So, the soil is there and river is there and lakes is there and all that, and the soil system is divided because now it is the underground, right. It is the underground system that I mean here. So, from precipitation water is coming in, it is moving into the vegetation system, and through evapotranspiration also some water is getting lost. It is interception is happening, it is moving towards the structural system. Again precipitation is again allowing water to flow into the structural system, that means lakes, rivers, soil moisture, everything is there. Okay. Now, this again can be uptaken by the vegetation system, right. So, from the rivers, from the lakes some water is being taken up, it is being intercepted, and some it is getting back into the vegetation system, or from the structural system it is getting evaporation and it is getting lost into the atmosphere. Now, precipitation is again happening, it is getting into the soil. If it is infiltration is happening and there is some storage that is happening structurally, so there is some depression, there is some storage, so it comes back into this, that is the structural system, or it can go to surface runoff and go into the lakes and go into the rivers and then go into the oceans. It gets infiltrated and it, the soil moisture and all that there. So, moisture supply, it comes back to the vegetation system. Vegetation system again through flow. What is through flow? That means precipitation is happening, it is not getting intercepted by the leaves and all, water is falling directly onto the whatever water is falling through the leaves and it is getting into the soil and all, that is called the through flow. So, through flow it is entering the soil system. So, this is much more processes are involved, many interactions are happening at these junctions, and this again controls the water chemistry, because everywhere that the water is being intercepted there is some interaction happening, there is some chemical interactions are happening, and that is changing the chemistry of the water. And these kind of processes and what chemistry is getting altered, we can actually use isotopic geochemistry to pinpoint the processes, right. Now, a very important very important concept is the factor of time. Okay. Now, as when I was discussing in the global water challenges and future vision to find solutions to those problems, I had mentioned this term called persistence, right. That is, how much time will a particular contaminant be there in that system, what is its effective exposure duration in that particular system. Now, in terms of water, every kind of water has its own residence time in the system. So, residence time is basically the time between a water particle's entry to a particular environment and its exit from that particular environment. Okay. Now, in catchment processes, it is extremely important that we understand what is the residence time, what is the renewal time of all kinds of water, because then only we will understand which kind of contaminant will persist, which kind of contaminant we can use as a tracer, and different kinds of applications of chemical tracers in this kind of analysis of contaminant transport, contaminant persistence and all that. So, world's ocean, how long they take to renew, it takes 2500 years. So, the residence time of water, if I take a water molecule and if I leave it in the ocean, okay, it will stay there for 2500 years. That is what it simply means in layman's language. So, residence time, the formula as I have showed, is the amount of water in a reservoir, that is in terms of a mass scale, that is either kg, gram. So, gram is a very small unit, it is mostly in terms of larger scale. So, kg or bigger tons and all that, and the flux, that is either into or output. Okay. So, flux into the reservoir, that is the amount, that is the mass per unit time, right. So, if I divide that, how much time will it actually take to fill the system or to get it out sourced from that system. Groundwater, groundwater, generally shallow groundwater is roughly 1400 years. Renewal time in groundwater is actually 1400 years. Polar ice is takes, of course, you must be knowing that it is dependent on the interglacial cycles and very long climatic controls. So, it can be thousands of years. So, here it is 9700 years as compared to water in lakes, that is which is only 17 years, then the water can again the entire water of lake gets refreshed and all that. So, there is new exchange and going on. Channel network. So, rivers, how much time water molecule spends in the rivers? It takes only 16 days. Okay. How much time is it there in the atmosphere? It is there for 8 days. How much time is water there in our systems? Biological water, it is there just for a few hours, right. So, that is residence time, and I will talk about residence time more when we discuss isotope geochemistry and how it is so important to understand and compare the residence times of water as compared to those particular metals or isotopic tools as tracers, because we are going to use them as tracers. So, we need to know what is their residence time as compared to the residence time of water in a particular environment such as lake or in ocean or in groundwater, etc. What is the threats to the water cycle? Do you think that there is any kind of changes that we are seeing in the current climate change that we are talking about? What is it that is changing? Because of course, as I have told you, water cycle is central to climate. Therefore, there are of course changes that is happening in the climate, that is changing the hydrological cycle and the feedbacks, the continuous feedbacks that is happening. So, the long term exchange between the glacier ice, that is the cryosphere, and the ocean, that determines the global sea level, right. So, heat is being exchanged, right, and mass is being exchanged. So, this balance maintains the global sea level, and I am people who are from the earth's science background, they must be knowing that we have something we call is the Milankovitch cycle. Okay. Now, what is the Milankovitch cycle? Milankovitch cycle is due to it can be broken down into 3 cycles. One which is the cycle or the obliquity of the earth. So, earth is moving around the sun in a oblique pathway, right, and the obliquity of that pathway has a change. So, it changes, and that changes are noted in thousands of years. So, due to that change in obliquity of earth's revolution around the sun, we see different climatic changes. Also, you must be knowing that the earth is slightly tilted, right. At the poles it is not that the, so if you have seen the earth, there is a slight tilt is there. So, the tilt of the earth is also the angle at which the tilt is there, that angle is also changing, right. Now, this change also influences the insulation. Okay. So, how much time is the sun's energy, how much sun rays is falling on a particular zone that we call on a particular in the northern hemisphere and the southern hemisphere, that is getting altered if the angle of tilt is changing. Also, the earth, there is a wobble around its axis, okay, that is also sometimes changing. So, this change in earth's wobbling, in earth's tilt, and in the obliquity pathway, this creates a huge difference and controls the climate, the very very long term climate. Okay. And therefore, we have seen glacial periods and interglacial periods to happen, and there has been much many glacial periods on earth, there has been many interglacial periods on earth in earth's history, and currently we are in a interglacial period. That means, currently we are in a warming period we will become much warmer, and again the climate will slowly move towards glaciation, where there will be large glaciers will be forming, because the climate will again go towards cooling. So, that is a natural cycle, okay, and that is that has happened in Earth's history many multiple times. And during these interglacial and glacial periods, of course, there is sea level rise and sea level fall. So, when the glaciers are forming, a lot of water is getting ice locked, right, at the polar regions. So, therefore, the sea level is falling. Many terrestrial water surface water is getting terrestrial locked. Okay, the glaciers on the land, they get locked into the land surfaces. So, the river discharges, they can fall, the river discharge, there is a significant drop in river discharges. So, that causes the sea level to fall down, and mostly it is because due to the growth of the polar ice caps. Just the opposite happens in the interglacial period. So, during the interglacial period, there will be warming, there will be a rise in the meltwater contribution from the glaciers, and via river discharge it will come down to the oceans. So, the sea levels will rise. Okay. So, this is some examples I have given, that the eustatic sea level is rising at a rate of 3 to 4 millimeters per year, and that is due to a combination of glacial meltwater and also due to the increase in volume due to the warming of the ocean. So, of course, that when anything is warmed, it increases, it expands. So, due to expansion of the oceans, there is a slight sea level rise. Now, what happens in a warmer climate? In a warmer climate, there will be more evaporation, more evapotranspiration activities, and that will intensify or accelerate the hydrological cycle. So, the wet regions are suddenly going to be much more wetter, and the dry regions will continue to become more and more drier. Right. So, it will be extremely intense even. So, I think we all are now seeing this kind of activities happening, that where it is raining, it suddenly starts raining, it rains heavily for a few hours duration or maybe a couple of days, and then for the rest of the time it is just not there. So, such intensification and the acceleration of hydrological cycle is a big threat to the hydrological cycle. It is not in terms of the water movement, but due to the movement of nutrients, due to the movement of pollutants, due to the movement of all other contaminants that is moving due to this accelerated and intensified hydrological cycle. And most of the time certain extreme events, we see cloudburst events, we will see landslides happening, we will see floods happening, or otherwise we will see droughts in other places where it is getting very dry, desertification happening, loss of life is happening. So, these kind of imbalances are happening due to climate change, and generally these these are already a lot of predictions are being made. There are global circulation models and climate projection models are they are done to understand the likelihoods of events, the likelihoods of extreme events, and to prepare ourselves better in our future. So, for future water security, for future food security, for management and disaster preparation, these kind of global circulation models and climate models, they are built and they inform us of what to expect in the near future. With this global water hydrological cycle, I come to the end of this lecture. In the next lecture, we will talk about catchment hydrology, and I will discuss how to calculate the few important terms that we will be using in catchment hydrology to understand groundwater and river water chemistry and surface water chemistry. Thank you all of you, and we will See you again.